That's what determines the ranking. Whoever does the hardest serves in second is you. 21 nonsense. Yeah, I'm just talking shit because I think I knew that one. I know. I know. So a lot of it was just stuff you already said in class. Short questions or stuff you said in class. Yeah, that's the thing.
Like 20 hours literally full.
I test. What? Who has a lunch?
I mean, maybe some very first question.
It was different.
How the concentration is busy.
The concentration doesn't vary spatially.
So it's always the same.
Oh, we're talking about that.
The thing is, you can't think of it as start because then if you try to do something started,
I'm confident that was right.
All right, everyone. Let's go ahead and get started. Had to borrow a watch today. Had to borrow a watch just because I forgot mine. Anyway, otherwise I'm going to live here forever. So, review session today, as you already are aware. So, homeworks are still being worked on. It's fine. Don't just wait till after class. See many of you take advantage of that, slip them through my door before 5, which is okay, don't worry about it. So I'll put the answers after 5. After that, I can't take any more. And again, the averages came out. You have now 3 times in a row the 93 average. I guess 92 in the first one. Again, higher. The next best class I had was 10 points less. So that's a very, very good thing. So the test is a lot harder than, I'm just kidding. I have written all the questions now, and so at times I will be bleeding like a fish in terms of what's on there. And now I also only have 4 pages of notes because stuff just isn't that bad, in all honesty, especially after you've done your homeworks. And so I loaded a little early, but then we can ask questions, and I brought things to throw at you. But there are actually no rocks inside, like candy. So anyway, we will have time for questions and answers. I can't stay too late because I got just some other random things I have to do. I will also prioritize getting the video up as fast as humanly possible. I will have it up tonight. I will also have your cheat sheets to you very quickly. I can't stay late because I want to finish the cheat sheet, make sure all the equations are there, and send that to you so you have that. Again, I reserve the right to change the cheat sheet at the last moment if I need to because there's something missing. I try not to do that, but every now and then I'm like, oh, I didn't include the van der Waals equation. Put it on there. So that may happen. Hopefully not. So, okay, well, so exam review, I've already gone over what's on the test, so I'm not inclined to do that again. If you want me to go over that one more time, just ask me at the end of this. And also a good insight into what, I know it's on the test, and I will sometimes say, here's something we covered, but I don't really care. And so you know what that means. I don't really have your homework. I've got your previous homeworks again, so we will end a little early in terms of Cindy. Anybody got any questions for me? A question?
Yeah, you've done a lot of derivations in class, so I was wondering if there's any other alternative derivations that you would want to do for certain state quantities like entropy that you didn't show in class.
We didn't do entropy. We haven't really done entropy yet.
Okay.
So you're kind of asking what's on the test.
Oh,
Now I have questions that are similar to homeworks, and you've had derivations on homeworks.
Right.
The question on the test will be very similar, but they will not be identical. I am not beyond doing that. If I feel like the class is not doing well, I might actually do that. That's really not you. I'm not trying to treat you different, and I don't like doing that. That's really pathetic. But so the derivational questions are very similar, but not identical to the ones you've had. But involve the exact same. When I say they're similar, it's the exact same principles. I already told you that the derivation. So there's two derivation questions at the end. One of them is going to be manipulate a equation of state to give me a residual volume or a compression factor. I already told you that. And the other one is a how does x change with y at constancy? And yes, I did set it up for you. I gave you the first step, like I said it would, because otherwise it's way too hard to know how to begin, and that's a test of your luck, not your knowledge. I don't do that. Okay, class business questions. If there's no class business questions, save other questions maybe after the show. And because you know I'm prone to prattling on and on and on. Okay, day one, covered the phenomenological model. Okay, now, the only time I've ever asked a question on day one, let me remind you what was there because we did it. The only time I've ever asked anything about day one was to define phenomenological. And I know I've already asked that question, so I'm not going to do it again. But just to remind you, what is this class about? Maybe that will help. I had a phenomenological model for pressure. Right? I said molecules hit a wall, and from that I got P times G is equal to energy. And many of you said that that had never really been told to you. Actually, the nRT does come out to be joules, so maybe you noticed it there. But that again was just something we discovered, but better was temperature. So temperature, and therefore, at minus 273.15 degrees Celsius, volume was 0 liters for a gas. And below that, you get negative volumes. So that's how people figured out that there are certain temperatures you can't go below. I remember learning that for the first time, thinking that was really nuts. And actually what happened is, because people have tried. Oh, excuse me. Imagine you have temperature versus like time, right? So you have an incredibly good refrigerator, freezer, whatever. We have devices that can get things really, really cold. And what you find is that as you decrease temperature, but you get to this point and it just flattens out. You can add more juice, you can add better coolants, you can add more coolants, you can wait longer, it never changes. It flattens out right there. So it does seem to be true. Okay, the things you can do with phenomenologicals, the theme of this class is you get this equation, and from here, remember this one, this was a linear equation. And you may be like, okay, well now I have something, I fit a line, and now I have this concept of temperature, which is nice and useful. Especially, if I want to freeze the reindeer that I just slaughtered. But no, you actually learn some much more deeper things from that. And which brought us to imperfect gases. Okay, this was day 2 actually. And because perfect gases you had in high school, and imperfect gases are different from perfect gases. Sorry, I should say more real. Sorry, that's bad wording on my part. They have volume and interaction. And I hate to say dipole interaction because it's dipole-induced dipole or induced dipole-induced dipole. Those are different types of interactions you can have that are pretty powerful. And I think I did say this, because I think of it. When we derived PD equals nRT, that wasn't a derivation. That was actually an example of a phenomenological model combining Boyle's terms and Avogadro's laws. And we just fit them together. That's not a real derivation. The derivation of the perfect gas law is possible. What you do is you determine fluctuations in density of a gas that doesn't interact or have volume, and you drop out PD equals nRT. It's done in grad school and it takes nearly an entire day, a derivation. So when I say that perfect gases, when PD equals nRT, means that gases don't have volume and they do not interact, it's because the proper derivation has that as part of the phenomenological model that results in the actual derivation of PD equals nRT. sounds simple, it's really for grad students. I usually do it for my grad students, but it's not going to happen. Okay, then I introduced two equations. Virial was the first one, and that was a PDM. Now remember that all of these questions, when it came to these real gas equations of state, I always had VM, volume per mole. And I do have you doing calculations on, not the virial, calculations means numbers, not derivations. I do have you doing a calculation on van der Waals and over VM. Now, I'm leaning towards, I'm sorry, I actually do have one more question to write, and I'm leaning towards doing something with this, with the virial. All right, so remember, virial is ultimately curve fitting. This is technically a Taylor series expanded in components of 1 over VM, and I know I can curve fit it. So this is going to work. You did do some questions with it, some derivations. You found residual volume, you found it was B, and you also found the compression factor, and that was more complicated, but whatever. So, so this is something I am leaning towards having a derivational question based on. And again, it would be like a residual volume or a compression factor. God, I do still like that, don't I? Now, what I didn't like about it, and this is why I'm telling you this, what I didn't like about it was I don't like curve fitting. Also, temperature-dependent parameters, that's just, you curve fit by a Taylor expansion, and then you put in adjustable parameters into the Taylor expansion, of course you can describe anything. That was not so much valuable to me. But that you can manipulate this to residual volumes or compression factors is something that shows me you understand how this stuff works. And that's because when it came to van der Waals, we kind of did that one to death. Usually I actually just using my notes to make certain I know. What am I doing? That's a D to me. Van der Waals. Now again, I'm going to use a lot of shorthand just because there's a lot to cover. And I teach this class too much, I have this memorized at this point. I'm pretty sure it's on our cheat sheet. And now, if every now and then, if I run out of room on a cheat sheet and I don't have room for an equation you need, it's part of the question. Now, I'm sorry, that's not, I'm not trying to hide that from you, it's just I couldn't fit it into the cheat sheet. Look out for that. That has not happened on this test, but it may happen on the next one. Okay, so van der Waals I liked more because we had A and B were not temperature dependent. That's more meaningful to me. There's not nearly as much curve fitting. What people did was they took real data from real gases, obviously you can only get real data from real gases, and they made the best fits to A and B as they could, and that's where the numbers in the table came from. You can imagine how much the engineers had to work to do this. It must have taken forever to do the curve fitting. It's much easier with this. Now, we derived what A meant and what B meant by algebra and doing limits. I feel that what I do sometimes is I make up my own van der Waals equation. Sometimes I make up my own van der Waals equation and ask for that. I'm not leaning towards that because I've done it too much in the past. But what else did we do? We did things like Z, which was the compression factor. VM over VM not, but that's to say that the real volume is not the same as the perfect volume, perfect gas volume, which is really the way we actually did it was we said, well, no, the volume is okay, it's the pressure that's not. And so that's how we did it. And so all I have to do is, if I ask this type of question, which I did, remember, you've got to get this thing, this whole thing, into this form. And I know that's RT-VM-P. And this ended up being very simple. So P times RT, so you can see it a little bit better. I'll do it this way. What did I just flip it? I didn't flip it because it's on the left side. I just accidentally flipped it. VM over RT. Okay, and so VM RT. I won't be a cheap date. I will be a cheap date, not an easy date right now. So I'm going to just multiply that by the whole thing. there we go. And again, this is all algebra. You should not screw up algebra. And remember, all right, there is another way, in case you ever wonder. I don't do this often, but it does work. A over RT. And there are alternative ways to do this. If you think you've screwed up, add numbers, 3, 5, 7, 9, 12, 13, and then do this math and then see whether it's the same over here. Just a little trick you could do if you ever think that you're having algebra problems. Sorry, that looks ugly. Okay, then we did residual volume. Okay, that's really Vm minus Vm naught. And then where you apply a limit of pressure going to 0. And the limit of pressure going into 0 means RT over PVM Okay, so don't forget that. In case you don't remember, which I bet is probably most of you, we're going to be able to replace PVM with RT. That was a necessary part of the derivation. All right, so now again, the trick is get this to look like that. That's the whole trick. So what I'm going to do is take P, I'm going to multiply it by Vm minus V, and then I'm going to divide by P. Is that right? Because then I'm going to have Vm minus V on one side. But wait, no, hold on. Sorry. I'm really sorry about this. I want to point out that this, I want to see what I really need to get. This is why I'm having a little bit of trouble. That I'm not looking at my notes. Vm, which is going to come from the equation, and Vm naught is going to be RT over P. Okay, now it's much more clear to me what I have to do. And I'm sorry for the messy board work. Let me just do a little board. Okay, so all right, the main thing again, I can't emphasize this enough. Get all of this left and right to get here. Don't add things. That doesn't make a lot of sense. I guess you could, but you're making an easy derivation hard. So I'm going to take P, and I'm going to multiply by Vm minus V, and I'm going to divide by P. Okay, so that's RT. Let's see how I did it before. Sorry. Let me do it like before. Sorry about that. P times RT over Vm minus V minus A over Vm squared. Oh, sorry. Vm squared bracket. Okay. So that's not hard. I got Vm minus V over here. And then I've got RT over P minus A Vm minus V over Vm squared. Okay, now I can see I've got, well, as you can see this, Vm minus RT over P. See, there you go, I've chased it out. All right, now several steps of algebra at once. Oh. See that? I didn't put the P there. Sorry about that. Okay, I'm going to do two steps of algebra at once. This is going to be A over PVM plus AB over PVM squared. Now, if you recall, this is our stopping point, kind of. The problem is I haven't applied the limit. So I'm going to write that out. Apply limit. And that makes this V res. And I'm not using proper notation, but I'm going to use this guy here. So because now remember, this is a big lesson and this is on the test in a weird way. It's hard to know what is happening here. Pressure's going to 0, but I make pressure go to 0 by increasing volume to infinity. And it's not clear which one wins. And so actually when you're doing like math, like really deep kind of math, or certain extra math classes, you know that when you have, maybe you saw this, maybe you didn't, but one of the things I learned in my more advanced math classes is like when you have something approaching 0 over something approaching 0, you want to just say it's 1. Mathematicians would tell you, no, you're not allowed to assume that, it's not necessarily true. So you can't say that one necessarily cancels the other, but you actually can, because we know that this is true. We've measured this, it's absolutely true. A over RT plus AD over RT dm. Oh, sorry, yeah, RT dm. Now, again, dm is going to infinity, and there, we're done. And remember, okay, yes, a gas expanding because pressure is going to zero, because that's how I made it go to zero, does make temperature go down, but I can warm it back up. There's nothing weird about that. There's nothing that says I can't do that. So this guy is a number, it's well behaved, and this guy, I can make it whatever I want. And there we go. Now I know the residual volume at whatever temperature. So this concept will come up as well as residual volumes. So do expect that. Okay. Notice I did that off the top of my head. No, I did do it off the top of my head. So I think you can do it too. So, okay, then we made a big change in this class, and wow, I've got a lot of time on my hands. We made a big change in my class. We then dropped all this perfect gas stuff, and now you can see perfect real gas, and you see why I went over it, even though like P equals nRT was boring. It's because I was able to incorporate it into some of this thermo stuff. So that's why I went over this, and you may have been kind of bored, but I think you see why I'm doing it. And of course, we start with the equal partition. I'll write it out. Equal partition theorem, which says that you get 1/2 RT times degree of freedom. I'll write that out. Okay, that's going to be a DOF from now on, and that's the U of, we'll work with the gas. Now this works for any material that exists. It's just easier to do gases. This is why I do gases. It's why I'm not so good at peeking with biochemists, because I want to do all thermo with gases because it's just infinitely easier. Okay, then degrees of freedom. Sorry, where are my notes? Okay, degrees of freedom. Everything can do 3 translations. Okay, now, if you have a linear molecule, remember, you add 2 rotations, and then nonlinear, you add 3 rotations. Now, notice that I've already excluded atoms. My word kind of fumbled when I did this last time, when I went over this. You can't have a linear argon, right? Argon's not linear. And argon is definitely not linear. So my Nobel gases, which obviously is what I'm talking about, 3 translations. 3 has RT is their energy, their internal energy. And then vibrations don't count. And remember, it's a little factoid, it's obviously not on the test. The reason that you have 3n minus 5 vibrations for linear is because they only have 2 rotations. Everything has 3n degrees of freedom, but you just subtract out 3 translations and 2 rotations from the 3m waves of motion to get the remaining vibrations, and then 3n minus 6. 3n is the total number of ways to move. But from that, we're going to subtract out the 3 translations and the 3 rotations for nonlinear molecules, and that's why the number of vibrations for methane is 3n minus 6. That's where that came from. I think it's one of those things that just got thrown at you. And remember, I said, we're going to do practical problems in this class. This is what this class is for. This isn't the thermodynamics of rocket engines. Vibrations just aren't going to count. Now, from this, I got a couple of things. Let's see. One was that, at constant T, the change in T is 0. Because right there, it actually could be, no, sorry, no, I'm being an idiot. Yeah, because of the equal partition theorem, because you've only got one variable here, well, this is a little bit of a variable. Remember, that's the thing that's hard to understand. For the most part, we have one variable, it's not changing, it's not changing. We also, I'm going to skip ahead a little bit, But I know that change in U is change in heat plus the change in work at constant V. This goes away. And therefore, the heat capacity, which is the change in heat over the change in temperature, is equal to the change in U with respect to temperature, as long as we're at constant V, right? Because the work goes away. There you go. That's how I was able to get that. Again, I'm skipping a little bit out of order. It's just that I've got these relationships right in front of me right now. So I just didn't see it a little bit later. What else do I want to say about that? And that also meant that I was able to, I'll just write out an example, like argon CD was 3 halves R. Because I just took the derivative with respect to T here. Excuse me. And then N2 was 5 halves R. And then we started seeing it wasn't perfect. And then methane should be 3R because it has 6 degrees of freedom. So 6 over 2 times RT is 3RT. But it was a little higher than that. And again, something I do kind of obsess over is because we're not really counting the degrees of freedom correctly. It just gets confusing the bigger the molecule gets, which is one of your homework questions. And I don't think that's actually on the test, but it could be on the final, so it's worth going over. Okay, so those are some things. Now remember that constant temperature, that is immediately true. So when I say constant temperature, you write dT is 0, and you write the change in U is 0. Adiabatic, it's a little harder. You write dQ is 0. You don't quite get you don't get another freebie there, but you at least got a point. Okay. Now, when we went over U, I first started with U here. That's what I first started with. And so I started with work. Sorry, what am I doing? No, I'll go ahead and write this down. I don't want you to confuse what I wrote up there with this. So remember that heat is hard to work with because I kind of just have to tell you 100 joules were added. Reversibly, irreversibly, it's kind of not going to matter. It's just 100 joules were added. So heat, I never had really a heck of a lot to say about, but work I did, because work's a human action. So, when humans get involved, when the human has to do the work, then the human has multiple choices on how to do the work, and now we have paths. And I know that work is path independent. I went through a pretty long explanation on how heat is path dependent. Work is as well. I just gave an example for work, and oddly something that's not path dependent, which is something I still just never really understood. I don't know that I need to. Okay, then we had to start introducing paths. First thing was that no matter what, the one thing I can always do is this. So remember, this is a force times distance, which is work. And because I will stick with gases just to make your life easier, and because that's how car engines work and that's how your power plant works, so I consider that the most relevant. So I like to stick with the pressure and volume form of force times distance. And IU pack fit up a minus sign. Yes, engineers, you were taught differently, and I think that's very strange not to. I don't like the minus sign, but if us people, what if we all spoke the same language and learned all the same units? Wouldn't that be much easier? I don't know why we don't do that. That kind of sucks. It'd be much better that way if we did. Okay, now what I can do is define irreversible, and hopefully you saw that. Okay, change in work. I know some of you engineers were a little nuts over my bad notation. Delta V. So I've integrated it. I've integrated this equation over VF minus, this is VF minus VI. That's pathetically obvious. So irreversible, what happened was I applied a constant external pressure. And I started at 1 atmosphere. I always start practically. Even like the question on engines, question 3, it was at 90 degrees initially. I looked it up. Most cars are operating at 90 degrees, so that's why I use that. Fuel's injected at 1 atmosphere, that's why I use 1 atmosphere. So the piston's at 1 atmosphere, I add 2 atmospheres, it compresses, and I can tell that that is correct because if pressure was changing, I couldn't use this equation because this isn't a constant. And it just, that doesn't work. So that's how I can tell that this is reversible. If I see that, hey, calculate it this way, that it's irreversible, because now I can connect how I did it with the equation. Again, this had to be held constant for this to be valid. I'll point out another example here in a moment. Now then we had the other path, which is reversible. Another extrema on how to do things, paths, 2 different paths. And that was when, of course, now again, no notation means interior pressure. So I kept the exterior pressure, actually slightly, if I'm going to do a compression, I kept it just very, very slightly higher than the interior pressure, such that I'll make this. Now notice that that means that the pressure is changing. Right, not changing is changing, because I know that as I close the piston, I know the pressure increases, and therefore I have to put a little bit more pressure on there. It's going up, 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 until I reach my 2 atmospheres, and that's when I chose to stop. Or that's when my machine stops, I don't know. Okay, so let's do the change in work. And that means I have to integrate VI, VF. I'll put the minus sign out here, PdV. And remember that when your integrand is hidden in what appears to be a static other variable, you can't ignore that. That is absolutely improper mathematical derivation. I over df. This is nRT. Change of v over d. And so the work in this case is minus n RT ln VF over VI. And these are not the same. We've worked this several times now to see that. Okay, now we've done isothermal and adiabatic. I've got the equations for work under both circumstances are on the cheat sheet, but let's just say, I think I even have them labeled as isothermal adiabatic. Or maybe not, I don't know, I'll double check. All right, let's say you have this equation, and I've asked about an adiabatic change, and give me work. And you instantly write this down. How can you know you're wrong, other than just trying to memorize it? I'm telling you, you don't have to memorize it. I just worked it. I wasn't looking at my notes. I didn't need to. So I don't need a cheat sheet, but I have one. I'm just saying, you were asked about an adiabatic change, and you just did this from memory, which again is bad. And I'm telling you, obviously, this is the wrong equation for work. What can tell you that? Temperature, right. Temperature has to be constant. I don't see a TI in there, but I know it's changing. So this cannot be correct because it requires it not to. That, again, that's why I was yapping so much about this. It's a constant. So that's how one of the ways I know I make mistakes. Just a little helpful guide that, when you make a lot of mistakes, it's fine as long as you know it and fix it. Who cares how you did it? Time's up, and then you've got everything fixed and everything's right, and you get an A. Okay, now at constant T. Okay, the way I set these up, generally I'm going to have to ask you about, I'll give you the stuff for work, and then you have to give me heat at constant T. Therefore, take change in work. I know I should have a big delta. Sorry, again, that's me using proper mathematical notation. I can't help it because I don't really care that much. So there you go. So now we've got work, heat, and U, which is 0. Delta T goes 0 because I told you that. And then now I've got H. And then next week we're going to start getting beyond H, which is U minus a variable that U depends on. How do I know that U is volume as a natural variable? Because of work, because it's PdV, right? There's that dV thing. I know that it's a natural variable. And so I want to get rid of that natural variable, so I multiply by the conjugate. So remember, so this just isn't out of nowhere. It's a Legendre transform. So I hope, if anything you get out of the class, I hope you find some of this stuff neat. And what always bothered me, although I didn't think about it too much because I was too little, is you're given this stuff. G is H minus TS, or delta G is delta H minus TS. And what the hell did that come from? And so why is H minus TS more important than H itself? Right? And we're getting there, but again, it's another Legendre transform. You're going to be doing lots of Legendre transforms. Now, we never told you about U, but now you know where H comes. H comes from the Legendre transform with U. Now, not only does H now have natural, it's energy, units, again, that's part of the test. Not only does H have to have the same units as U, so it's joules, not joules per mole. Now, I was working with one of you during office hours, and that person kept getting joules per mole. They're like, is that right? And I'm like, no, it should be joules. Joules per mole is not energy. So anyway, joules, and not a function of V, and also when you hold P constant, because that's its natural variable, H becomes heat like we always told you. And remember that we live in a world of constant pressure. It just came out that way. Okay, then we change in H. What's the change in U? What's the change in PV? And I told you that the trick there is you calculate the change in U, again, I'm using bad notation. And I'm saying since we're doing gases, again, another reason I do gases, because we can do this. This will almost universally be the easier way to do these questions. And as you know, when we look at adiabatic, we can see that this is actually a CPDT, but we're getting there in a second. Not much else to say about that. There were examples of where this could be PDV plus VDP. You did work one of those questions. It's rare. I don't normally have to do it that way. That was last problem set 3, which you're getting back to right now. Again, I promise I'm going to go. I need to make one alteration to the answer key, and it'll only take me a few minutes, and I'll have number 4 up in a minute. Okay. Also, sorry, I should add. Change in T equals 0, change in H is 0. And now, a question, All right, since we just started on entropy, this is as far as we got. This has all been isothermal. And how am I doing on time? Doing good. Then we had adiabatic. Adiabatic is the pain in the ass. All you can say is this. I mean, look how many, really isothermal. 1, 2, delta U is 0, 3. You only have to calculate work and heat like right now. God, that's easy. Adiabatic was unfortunately quite a bit more. And I wasn't even sure how to calculate U. And the reason that is that, let's see. All right, I've got my magic piston. The magic piston I'm always talking about is wrapped in glass wool. I'm going to work on it. I'm going to change its volume. All right, and I know that contributes to U, but temperature changes, and the equipartition theorem has part of that as well. So I've got two things changing U, and I'm not. Well, I think I can do one of them, but I can't. See, my equations for work were isothermal, and they don't apply anymore. So I don't know how to do the work. Heat, I'm not sure what the change in temperature is. If I did, I guess I could work it that way, but I don't have the change in work to begin with. See, I got a bloody mess. I've got a bloody mess with the simplest thing, the change in U. Right, because I've only got one thing now, change in U. And again, this is just, we've gone down a path, and we're going to do reversible, irreversible. We've gone down a path, and U has changed. This just represents that. But because U is path independent, the representation doesn't mean a lot really for T and V, but I can do this, and this is, it gets confused if you see this diagram again. I see that volume has increased. We'll go here. It doesn't matter which way I do it. Volume has increased, but temperature stayed the same. Right, yeah. It's just, see, temperature is always the same. Okay, now this guy, at this point we've covered heat capacity. I know I didn't say too much about it, but I see that it looks like I've cooled the thing by taking heat out, even though I can't. Remember, I've always said adiabatic is so strange. This leg can only be accomplished by taking heat out out of a device from which I cannot take heat out of. That's true. All right, regardless, I took heat out of the machine by following the weird path that doesn't exist at constant volume. Again, it's a temperature change at constant volume. How do I do U? Right, CVDT. And I'll stick with my partial type of notation, CVDT. Now, and again, remember, the whole adiabatic weirdness is that we're often expressing things as heat exchange when there's no heat exchange. What can you do? Again, it's like how U is exact, I don't understand. I mean, I can understand this, yes, but bigger picture, I don't get it at all. Okay, now we had to do the change in work plus the change in heat. Okay, well that's not there. There's the change in U, which is the change in CV. Again, I saw a ton of U. Use CV per mole instead of CV. I'm going to give you CV per mole because that's what you find on the internet. You have to multiply by moles. But it's still true that it's minus P. Okay, so let me just go ahead and do irreversible. So now I'm talking about work. And now that I'm talking about work, I have to do paths and irreversible. The thing you just did that you just loved. You had to simply integrate minus P, the exterior, which I gave you. And I have a choice of df minus di. Now, you just saw how to do that, so I'm not going to expand upon it. Now, of course, I had to give you this. I gave you CV per mole. I gave you moles. I gave you this. I probably did not give you that, unlikely. I gave you this. I have to. I gave you that. But now I've got one equation with two unknowns. I must have one unknown. I cannot solve an equation with one equation with two unknowns. That's information theory for you. It can't be done. But the trick was to know that because I'm going to be friendly, I'm going to put VF. VF can be put in the form of TF by T equals nRT. You then inserted that in here, then you had one equation with one unknown TF, you got the change in T. Started out looking the simplest, and ended up being the hardest. Now, I don't like putting these on tests. I am not inclined to put adiabatic irreversible, give me U, H, T, W, Q. I'm not inclined to that. If I do, it won't be one of those, give me all, remember, 12 variables. I won't ask for that, it's too much. Because I'm testing your ability to use a calculator. I don't really value that so much. Now, if I ask adiabatic equations, I'll simplify it. I'll keep it down to just a little tiny bit. But I won't do the whole full-blown thing, where I ask every thermodynamic variable. Now, I am prone to do that with all the others. But again, it's just, I don't want to see how likely are you to accidentally press 3 as opposed to 4 on your calculator. I don't care about that. And I do it all the time. But actually, last semester I was really bad. I was really distracted, had a lot of stuff to do. So every time I gave a hint, I got it wrong. And it was just not slip of the finger. Okay, reversible. Okay, let me go through that again. And I did once ask people to derive this on a test. And again, once I do something once, I tend not to do it again. I can't promise that, but it wasn't really hard. Watch this new notes. Okay, I had CV EP is now PDV. Oh, almost forgot my minus sign. Right, therefore, I've got CV change in T is NR E over D. Okay, therefore, I won't write therefore anymore. Remember that if you're going to integrate this with respect to T, you can't have T's over here either. You can't do that. Or unless you know some crazy math tricks I don't. When you integrate, all the variables have to be there on the right side. I'm missing a minus. Sorry. B over D. Okay, let's integrate. And this will come up one more time, but remember, that might decide limits on one side, it actually decides the limits on the other side. It's very trivial here, TI, TF. Whatever temperature this is that same initial volume for that state. Whatever final temperature you have, that will be the volume that occurs at that state. It will come up later. Okay, now therefore, I've got, let's see, you know what I'm going to do here is, there's a neat trick actually. What you can do is actually get rid of the minus sign and switch the limits. It's just another neat way to do this. I guess I won't do that now. What I'm going to have is, I'm going to do minus CV. This is how I did it in class. I actually wanted to change it up, but I unfortunately got too far. TF over TI is equal to NR. No, I already did the NR. LNDF over by PI. Sorry, how much time? Oh, God, okay, used too much time. Okay, again, identities that you should know, that if you need, I will provide them regardless. Just read my proposal program. Anyway. Okay, so I switched them. L and the F over the I. One thing I always remember in case I slip is that the T's and F's are I over F is F over I. Just in case I screw up, this is one of the ways I check. As I said before, natural log of A is natural log of A, so I got TI over TF, CD to DN, CD over NR. And now remember, I told you I do not like tricks, but it's too tempting. Remember, this is the CV per moles times moles divided by moles over R, meaning you can do this CV per mole over R. It's a lot faster. I hate tricks, but that's just too much to pass up. So when I ask an adiabatic reversible, you've got the correct these things, and you can, anyway, you plug in numbers. Now, in terms of calculator questions, I got 3 total, a little bit less, one less than normal. It's just what I did, what can I say? The tests are different every time, I don't always know how they come out. Okay, so now that you have the change in temperature, you've got the change in U, CD, change in temperature. Remember, the point of this is you got the change in temperature, I had to give you this. Now, the only other thing is now you got the, now that's the change in work, because I've asked you that. Then I got the change in H, which is CV dt. That's the change in U plus NR change in temperature. Because I just covered that, that's CV plus NR change in temperature, which is happens to be CP dt. Okay. So, and change in S, by the way, we haven't done that. Okay, last bit. Joule and Joule-Thomson. All right, we're now into pretty much this week. Joule-Thomson. Okay. I'm sorry, I have to think about the spelling. So what that was, remember that Joule was doing the TDP constant U. And Joule-Thomson was doing the TDP at constant H. And we were able to relate them to the change in U with volume and the change in enthalpy with pressure. So there was relationships between them. Some of you may say, well, oh, do we have to derive that whole, this whole maybe constant H for Joule-Thomson? All right, you saw me try 3 times and screw it up. All right, when that happens, no, I won't put it on the test. Because that's stupid. I really regret that I did that. So I would not have, just so you get to know me better, because you've got 3 more tests with me. When I screw up something massively, I'm usually going to take it off the test. Now, in terms of relating this to dUdV at constant T and dHdP at constant T, I think that's too much to ask. It's just too many steps. And I think just most of you you're going to get stuck. And there's no value to that, none whatsoever. It'd be great if you can do it, but it's just, you're under too much pressure. One thing is, though, I can certainly ask word questions. I can ask you, I love this one. Okay, what does this mean? You say, well, you change volume, and you measured how the temperature changed, and you did it by not changing heat or work. All right, now again, this is a mathematical expression, but notice that I can describe it in actions, with devices, with gases, with pressures and volumes. I'm inclined to ask those kinds of questions, I'm not saying that I did. Now, last bit that I'm done is, and I need to be done, all right, what was neat was that these were both done under adiabatic conditions. So remember I was making a bit of a deal about how these guys were done outside of the very dogmatic constant temperature, reversible, irreversible, adiabatic, reversible, irreversible. So I was thinking, okay, they were adiabatic, but were they reversible or irreversible? I started thinking about that. Now think of Joule Thomson's easier. Okay, it was a compression and there was an expansion, whatever, at constant pressure. What is that? Irreversible or reversible? Irreversible. Okay, now, is it not possible for me to have done that such that my pressure was just basically the same as the internal pressure on both sides of that little dividing zeolite thing? Could I have not compressed and expanded at essentially the same pressure inside? Could I not have done that? Yes, I could have. So, it's constant, but the outside is the inside. All right, I ask again, what is that, reversible or irreversible? Which is it? Both. Right, the answer is both. They're both happening at the same time. The answer is, it's a new path. It's not irreversible or reversible, it's a new path that kept enthalpy constant. Not temperature, not heat, but enthalpy, at different paths. So there's multiple paths. The same is true for Joule Thomson. So you made a sudden change, right? Remember you had pressure and connected to a vacuum, and then you turn on the valve. That's a sudden change in pressure, right? Reversible, irreversible? Irreversible. Now, hold on. Constant exterior pressure. As the gas filled that other valve, did the pressure stay constant? Did it? It's finite, right? Of course, here's a valve, this is an atmosphere, this is under vacuum, half an atmosphere, half an atmosphere. The pressure changed. It was a sudden change, but the pressure wasn't constant. It's neither reversible or irreversible. Okay, last bit, sorry, Carnot cycle, net negative work, no entropy change. I do have a question on it related to this. All right, so remember that what's important about the Carnot cycle is that it is a perfect engine because no entropy is changed and is fully reversible. Okay, but it was not fully efficient. So it just shows you, due to nature screwing with us, you can build a perfect engine, a fully reversible engine, and yet it will not, except under really kind of crazy circumstances, it's never going to be fully efficient. Now we did do entropy as heat over temperature. We're not going there, we're not ready yet. I barely introduced that concept, just enough to show you that the Carnot cycle had no entropy change, and I'm done. Oh God, your homework. Sorry.